All right, guys, time to focus.
No.
Time to begin.
So it is CHEM364, right?
And waiting for you to be done.
Yeah, something about this midterm and some problems that you probably hate in the homeworks can be potentially solved by MATLAB. Before we do this side viewing of doing several applications by MATLAB, which in truth can be a little more complicated. This bypass adds additional complication, but add your skills and make you more prepared to the next journeys in your life. So there are several, I think 6 presentations, and they will be needed for all of us to complete projects which you voted and elected as a replacement of an exam.
Yes, yeah, that's correct.
Right now we have 3 well-respected guests, but when you will be presenting final projects, the amount of guests will be substantially more, and they will be enthusiastically asking questions. And although I will give a warning that it is presentations of results only, they still will be asking about methods. So in some sense, you are doing dry run how to answer questions of audience during your finals.
Right.
They will ask how the code is working, why you believe that it works. So the here are the presenters and subjects. The intended time for presentation is 5 minutes. If you go over, I will try go and to the stage and kick you from the stage. But 5 times 6 is 30 minutes, so we have about 4 minutes for questions. Right? You're very welcome to ask, please, your classmates with questions. What else? Here is where we are in class, and let me give a little warning. Unfortunately, by the nature of our academic relations, we need to do assignments, right? And the next assignment is due on Monday. So it will be based on the questions and based on the way how the listeners take what presenter is giving. So basically, it is a way to stimulate you taking notes from presenter. Please try to answer it in writing, preferably in typing in Microsoft Word and with equations, right? If possible at all.
And then print it out.
No, just send us an email. Okay, so your slides all are here. The first one is Samuel Stevens. So
You got this, King.
Looking at the homework, I think I answered all but one question.
I tried really hard to include the answers to the homework questions, but I don't know if I did. So
I forgot to take a look at what all I needed to answer, and so but I think I did it fairly good.
yeah, I need a deep breath.
We're just chilling, straight vibes. Microphone up.
this green thing, pick up.
Okay. So yeah, principles of wave propagation, or wave packet propagation, sorry, momentum operator, evolution operator. So wave packet propagation is the unit of wave that travels together and it can be composed of both real and imaginary numbers. It's referenced as an infinite set of sinusoidal waves with different phases and amplitudes. So wave packet in the MATLAB code is right here. I believe it was codes like there are lines like 71 through 76. And it just kind of had side note equals, I guess you can read it and I'll explain. I guess more of just the equation here in a second. But the P naught is a little more important, I feel like, when it comes to the code, because it represents your distance traveled and how far the code has to run to its finish. And so large numbers go further, negatives go in the opposite direction of positives. So your principles of your wave packet propagation. You have the top equation, which is your wave packet propagation equation with your sine out of x t plus delta t equals your e to the negative 1 over h bar Hamiltonian times your change in time and times your wave or your initial. psi x of t, which is your transform of your wave function to the future, which is what the x t plus delta t is. To figure out what your Hamiltonian is, it's the kinetic plus your potential energy, with your potential being rho hat squared over 2m, which has to be can be transmitted into a vector, not vector, matrix. That's the because yeah, your Hamiltonian is dependent on your momentum operator, which is the rho hat. Rho hat also measures the, I believe it's the density in the Cartesian plane.
Probably you wanted to say momentum.
I said, yeah, momentum operator, momentum. Yeah, p hats. I might have it wrong. I could have sworn p hats. Momentum measures the density in the Cartesian plane. So yeah, so you run a matrix, which I guess, sorry, this is the code in MATLAB for your momentum operator, or momentum. And so I couldn't get this really well, like, typed out, but it's, you run your matrix to get your P naught in vector form, which is just going to be your change in your distance and then times over varying initial positions, which when it calculates out, you end up being able to plug back into your Hamiltonian equation, and then plugging your Hamiltonian into your wave function and figure it out to get your future equation. Which then allows us to figure out what our evolution, which figures out our evolution operator, which is your psi x of t equals your u times psi of the past, with u being e to the negative I s over h bar, which is the action that brings your the past to the future. With the code here being like 160, with your, this is your momentum operator, which is h bar times k, with k. It's supposed to, I believe it represents all values of, what was it? Here. K represents, I believe, just all values that can be like represent, so all the integers. And then matrix, it makes sense, matrix right here with your diagonal and your x, and leave. For this slide. You run it in MATLAB, this is what we start with. And then once you like hit enter and allow it to run, it ends up being able to kind of expand and contract, getting our final probability over time. And then just more figures and I guess view of it, your distributions.
Excellent timing.
Perfect.
He was just about to kick you out.
I was like, I'm getting to the end of it.
So, any questions to?
I have a question.
Yes, please,
If
Patricia.
you go back to the evolution operator, you wrote S. What is S?
Let's see. I might have messed up what S is supposed to be, and that might be supposed to be I. I might have messed that up. I don't know. I mean,
Yes, yeah.
solid.
You saw something?
You just don't want to give it this sense.
Oh, it needs to be presented so everyone can see it. Collectively.
Yeah, I don't know.
Where's our, what S?
So anyone from the class would
over H bar.
we were speaking about during first meetings in the class in August and September.
Oh, is that supposed to be
The answer is written there.
is it the detail?
No. Patricia is asking about letter S,
Mm-hmm.
and then in brackets, just read what is written in brackets right after the equation.
Oh, the action that brings the passage.
So the first word is enough.
Action.
Period. More questions to them? Let's know that he did show only the first method when, which applies only for free space. Right?
Not in the
So just so we will not be confused. Why people use the word wave packet instead of wave function? What is wrong with wave function?
Isn't wave function kind of like constricting, while wave packet is a little more broad? Is that a good explanation of it? Probably not what you're looking
They're equivalent.
for. I don't know then.
Me too. Wave packet typically moves somewhere. It is a superposition of many.
Oh, well, wave function is just like a,
It also can be moving, so it's like when we put in an accent on a specific feature. Why do you want to propagate wave packet with wave function forward in time? Which benefit do you get?
that's very,
Why do you need future? Actually, answer is accepted, but
why do we need to be able to look, so we can make like a good prediction of.
Okay,
what
yes,
is gonna
enough.
happen?
let's thank. In the same time, the next presenter is who? Is Melody.
Beautiful. Okay. So. You're okay. You're good. I can see
I
it.
can see the.
Okay.
It's not good.
Fine.
You ready?
Yes.
Okay, so we're here to talk about commutation and conversion of operators. So to start with, we're going to talk about the commutation of position and momentum specifically. So the commutation basically tells you it tells you whether or not two quantities can be measured at the same time. And if they can't, then it tells you the extent to which that they can't be measured at the same time. Looking at the top, this is just a general example. If the commutation ends up being 0, then they can be observed at the same time. So looking at position and momentum, we assume that that P is an operator operating on the wave function side. So we add in the operator here, and then you write out the commutation, which simplifies to negative I h bar times the wave function. I don't know how to, okay, there we go. So since we just did an assumption, you know, that the wave function is there, if we take that out, we just simplify it down to negative I times h bar, which is not equal to 0. Therefore, position and momentum can't be observed at the same time, which is basically the principle behind the Heisenberg uncertainty. So next, talking about the conversion between operators. So originally we are starting with the position operator in position space, which is a little difficult to think about. So we need to convert it over to the position operator in position or Cartesian space. The momentum operator in momentum space is a diagonal matrix. So to convert it over to being in position space, we need to convert both the columns in the matrix and the rows into the other side, basically, which we do using a Laplace transform once from the front to account for I believe it's the columns in the front. So this accounts for switching over the columns, and then in the back, this accounts for switching over the rows. So both W prime, which is this little function here, and W, which is right here, they are matrix transforming state functions. So they can do that conversion. Oh. Okay, so in MATLAB, this is the depiction of the position operator, which is just done using the command match position operator, which as you can see, it's just expands in a straight line. And then what we're more interested in is the momentum operator. So this is two different versions of the momentum operator, one using the command px and one using px3, which I have a description on the next slide. But as you can see, the difference between these two is this one has basically a lot more noise. So this one it's a lot more straight and easy to understand. And so you can use these in different ways to do the commutation between position and momentum. Okay, so this is the commutation using the two different methods. So on this side, we have the PX, which is the conversion that I talked about in the other slide. So that's just using the matrix transforming state functions to convert it over. And then this method basically uses a Toeplitz matrix, which is basically it does what Sam did in his slide that he wrote out by hand. It implements the finite differences. And so I don't 100% understand it, but that's my understanding of it. So we in the MATLAB code, it's basically the same thing. Does the commutation, except with this one it's px, and in this one it's px3, and then you do the mesh of the imaginary component, because the commutation of position and momentum should give you an imaginary unit. So on this slide, if you look at this graph on the right side, it's the real part, which is at 0, which is basically proof that it gives an imaginary unit. And then one other thing to note is that this, which is basically the zoomed in version of the commutation, along the diagonal, it's not 0 because it's the unit matrix times the commutation, which is also not 0. The end.
Okay. Next presentation on the 1 minute overtime. What are the questions?
Is W prime the derivative of W, or is it just?
So the difference between them is
Negative.
the negative.
Okay, so I was gonna say it's the derivative question.
Okay, I have a question, Madam. Sorry, if you go back to where you found the commutation of position and momentum, you wrote IH acting on the wave function. That's
Which part?
that part,
This one?
yes.
So that it's just multiplied by it.
Okay. Yeah. More, David, please.
So here, you describe the commutation between position and momentum in one dimension. How would we expand this to more dimensions?
I don't know. Great question. Yeah, I don't have
You
an
don't need
answer
to,
for that one.
just think what seems natural.
Squares? I don't know. That doesn't really make sense. I don't know.
Same for each dimension, right? same for each dimension, and commutation says 0 if you try to commute variables from different dimensions between each other. That's what you wanted to hear, right? Yeah, basically.
Okay,
So you and you wanted to say,
yeah.
okay.
Yeah, that's what she meant.
No.
Oh.
Quick one. You did show in your momentum operator the elements which are non-zero and very far from the diagonal. What are they and why they're not zero?
So in this slide,
No. Momentum operator. Before commutation. Yeah, here. So this element.
okay,
What-
it has to do with the boundary conditions.
I think it is enough.
Okay,
Correct answer.
Nice.
So the next presenter is Patricia, so we'll just stop this presentation and bring up yours. Maybe quick, escape. In the PowerPoint, select.
All the tops, yeah. Having heart palpitations.
hello,
Hello.
hi Patricia. Kind of nervous still.
It's okay.
Me too. So this is my presentation. I had a lot of topics, so I could not bring them together in one presentation like that. So the first one I'll be talking about the initial conditions for a Gaussian wave function. I would really love to show a video showing how wave function changes with changes in initial conditions, but I struggle with that a lot. So I was stuck with having the initial conditions. This is the initial conditions. If we plot this in our wave function, this is what we're likely to get with our initial position starting at 30 and our initial momentum starting at 90. If you increase the momentum, it would increase the velocity, and you would notice that the wave function moves more, oscillates more faster. I would have loved to show that, but I said earlier I could not navigate how to do the video, so enjoy this. Sorry. So, and this is the equation for the wave function in which we have the equation for our plane wave and our Gaussian distribution and our normalization. If you hear in this wave function, the wave equation, the initial position, the initial wave function was normalized twice. I really do not understand the concept of normalizing twice, so this is the equation for the initial position. And alternative methods to compute quantum dynamics. We have three methods for computing quantum dynamics, and the first one we have is the momentum operator, the momentum in momentum space and propagated in momentum space. So based on the Collins symmetry gave us, actually was just really there for the first part, how to convert alternative methods. So I just and the second one is the momentum is transformed to coordinate space and wave function is propagated in coordinate space. This is just to take the momentum operator, convert it to position space using the Fourier transform. And also you plot the new momentum into the Hamiltonian and evolution operator. And after that, you iterate the wave functions with your evolution operator. Then the third one is the momentum operator is defined in position space and wave function is propagated coordinate space. This is just turning your into a matrix, yes, because this is the code for turning your momentum operation into matrix. Then you try to plug in the momentum operator into your Hamiltonian operation and your Hamiltonian operation and your evolution operator. I would also say that these three methods, they actually use the same principles for Hamiltonian operation and operator and evolution operator, but they differ in their initial definition of momentum operator. Okay, so the discrete representation of wave function. I tried to, from the code to, from my research of discrete representation of wave function, I was able to see that this continuous wave function is split into rectangular bars. Discrete. I tried to make it like that, but I wasn't able to turn the continuous flow into a discrete. So I had to make use of this, in which our wave function was given as 3D, a quadratic and a linear. A quadratic and a linear, yes. So this discrete representation is just about converting your continuous wave function into discrete. It has a rectangular chord inside. And can we normalize our discrete wave function? Currently, yes, we can. And apart from, and I think this is the normalization of our discrete wave function, because from our initial wave function, this already is a normalization factor, is a normalization. So to double normalize, I still don't get the concept of double normalizations. It's just to ensure that the probability density equals 1. And size stimulation versus size time stimulation. So, as we know, the last class, Dimitri explained that as we go on from left to right, oscillations, and the wave function moves from left to right, we notice that there is a repeat of this wave function from the other side. That means if this reflects here, I try to do that, there should be something that comes out that reflects, that continues like this. So I think that was the one that gave us the, within the boundaries, you notice a replica, a repeat of the oscillations within the boundaries. Thank you.
Please join me. Thank you, Patricia. Any questions? In your last slide, your Wavepacket starts reappearing on other side, right?
Yes.
Once.
Yeah.
Almost.
Yeah.
So, how many times you need to increase your initial momentum so that it will reappear 3 times?
How many times?
No.
3 times.
Yes, that's correct. If there are more questions, let's take Patricia once again. So the next presenter is Ava. And she will likely teach us.
I might not.
About
So much.
what one can, how to make correlation between computation of this code and experiments.
Yes. Yeah, so my presentation, my current understanding of the information is broad term about observables. Oh, Dimitri, this doesn't have my first slide in it.
It doesn't?
No. My slide about what observables are.
Is it a big problem? Should we find it, or you better spell it by words?
I can spell it by words.
I think you need to be because right?
Pretty sure it's not like out of order, essentially.
Because I sent one on Wednesday and then one yesterday.
Is this one better? Still too bad.
Is it slide 3?
I can just explain it with words.
Let's do last. It will be better just to go ahead.
Ignore that. So I'm talking about observables, which like examples of that include spin or velocity or momentum. We're focusing mostly on
Share screen again.
what?
Oh,
Oh, boy. Oh, boy, oh, boy.
Share, just share everything. Okay, now go back to presentation.
Is it fixed?
yes.
So we're focusing mostly on position and momentum on those observables specifically. So before you kind of go through and I guess solve or compute any of your expectation values, you have to accumulate them. So we're looking at it for the whole trajectory, which is, I guess, the time or the amount that you're kind of looking at it or following it. And then I have kind of code on one side and then the English translation on the right. So essentially what we're doing here is we are adding up the product of our X value and the probability distribution. So the AVG3 and the prob 3, I think, is for the fact that this is like kind of like the third method, which is why it's 3 versus like 1 or 2. And then just AVG sort of in general, which we see here without the S is the average position. So this is us accumulating the values. So this list, this makes it longer than just the AVGS3 itself. And so what we're sort of summing the average values to get the expectation value. And then this is not in
Keep
the order.
speaking.
But this is about saving. So saving the data that you have kind of in MATLAB. This is beneficial because then if you like clear out your variables or you leave MATLAB, you can reload them back in and use them for later. It's a pretty simple code. You can say save and you do an ASCII and then whatever your name of your file is, you say that twice. So it could be average or whatever that you want it to be. So then when it comes to the computation of the expectation values, it's a little, there's different formulas for position versus momentum. So for position, this is the formula that we're kind of more familiar with. Where you have the conjugate, complex conjugate of your functions. We saw that code earlier. That was the last slide that I showed. And then the formula is similar, but you go in with your momentum operator rather than the position. So it's kind of similar. The code is not too different. It's the sort of AVE part itself is similar. The norm, so that's with the normalization, which you kind of know, and Patricia talked a bit about normalization in her presentation. So one thing to notice is the system has both real and imaginary parts. When you are wanting to plot something like I have on the right, you want to plot just the real part. That's a very simple command. You just have real and then whatever your function or whatever it is you're trying to plot. If you plot just the imaginary part, it's just kind of noisy. It's not really a function that I think is helpful. So then you also can do expectation values of energy. This is just sort of the commands I have listed depending on what method you're looking at. Then at bottom is the, again, formula that kind of math-minded people are a bit more familiar with that idea. And again, this is us normalizing it. It's like the psi star times psi and that. And then, so Melody kind of talked about this a bit too, the Heisenberg's uncertainty principle. Sam also likes, this is his favorite subject. Well, you can't know position and momentum of a particle at the same exact time. And then I just have the formulas for the uncertainty of position and then the uncertainty of momentum. They are pretty similar. It just kind of depends on if you're looking at momentum or position at that time.
Conclusions?
So my slides are at.
Question number one, what are your conclusions?
What are my conclusions? My conclusions are. I mean, besides just the formulas that I have listed. What question am I trying to
If
make?
you don't know what, if you like freezing and don't know what to answer, just repeat your introductory slide by your own words and say everything you wanted was confirmed.
Well, this is just me going through what observables are. And observables are things such as position and momentum, and this is how we can measure them.
Okay, you have a second circle, good. So. Of which objects you may want to predict in your research? How to connect what you taught us right now to the research that you want to eventually do or you need to do?
I mean, you can look at the position of like a molecule or the electrons around it.
Okay, or maybe group,
Okay.
the parts.
Yeah, as a group we use.
Okay, that's good. That's good. More questions, please.
On your saving variable slide,
Yes.
you talk about how you need to do save, then an option which you're using ASCII2, and then you have two expectations written. What is the difference between the two expectations?
That's a good question. I just know that when we save the file, you have to put the file name. Because you're saving the file and then you're saving it under that same file name.
So
There is one a word that starts with letter V.
that would make this conversation much better.
And where this starts with the V.
And it is-
Variable.
Yeah.
Variable is the correct word.
So
So you have the file, the name you're saving it as, and then the variable you're saving.
makes sense.
More questions to Eva? Let's take everyone. Sorry for.
Yeah.
Calling
me out.
So
It
we
was
have two more teachings to absorb.
Elsa's gonna.
5 minutes left.
Something.
For rhetoric.
All right. No nonsense theme for this no nonsense topic. All right, so we're talking about a few things, like real and imaginary parts of a wave packet, potential and probability distribution, visualizing observables and bundling those observables, and then making movies out of our stuff. So these are the real and imaginary parts of a wave packet. This is the code that plots the position against the real part of our wave function or our wave packet, and then the imaginary part of the wave packet. And then this kind of like square root function, I guess, is this yellow line that describes like the overall magnitude of the probability distribution of our wave function, kind of just to make calculations easier from what I've heard. So, yeah, the blue line is the real part, orange line is the imaginary part. I spent a long time trying to figure out how to describe the difference between them. But apparently, the imaginary part is no less real than the real part.
That makes sense.
I've seen on one forum, somebody said that one represented the amplitude and one represented the frequency, but I don't know. I don't understand how to differentiate between the two, but that's how you visualize them. So then I forgot to put the code up on here of what makes this graph pop up. Here we have a graph of probability against the coordinate or the position of the wave packet. There are 3 lines because there are 3 different methods of finding all these things, like Patricia talked about before, where momentum is defined in momentum space and propagated in momentum space, where it's transferred to coordinate space and propagated in coordinate space, and then I think where it's based on the derivative of coordinate space and then propagated in coordinate space. I also just realized earlier in the class that I don't really understand why this is a flat line compared to all the other ones. I went back way in the code because I forgot to put the code in here. And this line right here is based off of V in the code, the potential. And the potential of this wave packet in our base code is always going to be 0 because the wave packet is in free space. So that's my best explanation for that. But a better example of the 3 different methods are these 2 graphs. There are actually 3 lines in all of these, but they're really close together in this one. And the red and the dashed lines totally overlap each other in the second. But this is how we bundle these different observables like distribution and coordinate or position, and then kind of I guess a 3D view of time and position against the probability distribution, where we start off with figure, which makes a new figure, and then you can add new panels by creating different subplots, and that's where you define what you want to graph, and then you can add your labels and whatnot. So then to visualize our wave packet with a movie, first we need to make sure that the file saves as an AVI file. I think it starts off as a .mp4 file in the code that we're given. But if you change it to AVI and you need to add hold off also after you define what your video is going to be. Your video name is vid object 1, and it's going to, I kind of started talking about this out of order, sorry. But so we're making a movie with video writer defined by video object. So here we are starting vid object 1. We're starting with hold off so that we can compound all of this data onto the graph as it goes without getting rid of the previous data. And then you have all the code, describing, it's a couple hundred lines describing the wave packet. It ends it here, and then you need to add close vid object 1. So the program knows when to add that movie, when the AVI file is finished, I guess. And then when you run it, it should save as whatever you name in purple up there. So once you have that AVI file, then it's super easy. It just saves it to your computer, wherever the rest of your MATLAB files are. Go to YouTube, go to create, upload a video, and then from there, you just follow the instructions on YouTube, super easy. And then I did manage to figure out how to put a video into mine, because I had to. But yeah, that's what our wave packet looks like. So, Anna.
Any questions to Fred? Questions one, questions two, questions
Fred,
three.
was like the vid object in the end of the code, is that already in the code or did you have to type that in yourself?
I believe it is. I can't really remember, to be honest, but I think the only thing, well, no, I don't know how to go back. Yes, I think the only thing that I actually had to change was the name up here in
API.
purple. It's like some crazy long name from what I remember. Like to start off with,
Yeah.
it might not be, but so you just need to edit it, change it to AVI, and then I think I did have to add the hold off.
Yeah, and I added that too. Okay,
But then I guess if that's not there, then you should definitely add that there. Yeah.
okay.
So. All right.
Okay,
Good.
more questions? No?
No.
Let's take a break right here. So definitely there will be no time to ask questions to Elsa,
Yeah,
but she needs
Well-
to present it quickly.
okay, all right.
You got it.
No pressure.
Pressure. Not like we have to go to class or something.
We have class in 8 minutes.
Yeah. So. Already going so well, it's okay. So I did Wavepacket applications, in like the MATLAB code. So my first one is the application. The finite box symmetry, did you put that one in?
You did appear naturally.
Okay.
Keep going.
The wave packet is gonna be constrained to the bounds of like the bottom part of the green, so this part here. And it'll oscillate back and forth until it creates enough energy to escape the box. So U1 and U2 are gonna be here and here, and then this is gonna be U3. Is that, yeah? Yeah, so this is part of the code in MATLAB that applies to this. The 5.9 value is the continuum wave function value for hydrogen, I believe. And then your L is going to be the number of hydrogens that are interacting within the function. And then dx, I believe, is the amount of measurements that are going to be made. So then this is the application to an infinite box, and then this function will move and like flatten out as it moves. And so it'll move continuously in a free space. And it's kind of related to the time independent Schrodinger equation. Where K is the square root of 2me divided by h bar squared. This function can model a chemical reaction, and it reacts infinitely to maintain equilibrium, I believe. So this is an application to a barrier. It's not supposed to say continued, and the graphs that are displayed are hypothetical back reaction that's constrained to the periodic boundary conditions. Without the conditions, it'll continue to react to equilibrium. And then this is the harmonic oscillator one, and in this one, the green function will move back and forth under the bound of the red curve. So the norm squared of this function is a probability density that a particle or particles in a particular state will be measured to have a given position or momentum. The narrower the wave packet is, the better like localized the position is, and the larger the spread in the momentum of the wave. And so that's how it can be related to momentum, and at selected times, the probability density resembles an oscillator distribution function. So wave packets can be applied to observables such as position momentum and chemical reaction equilibria. It can aid in determining the position or the momentum of a particle or particles in a particular state.
Okay, please give me. Okay. Anyone that require any specific aspect of our presentation or to ask a strong question, let's postpone it. Okay, because we all need to.
Think of my toughest questions.
Let me focus on the last and make it simple.
Yeah.
Ending meeting.
Meeting is done.